Hello everyone. Welcome to my talk on the impact of intersatellite connectivity in large mega constellations. These constellations consist of thousands of low Earth orbit or LEO satellites and aim to beam internet from space. SpaceX Starlink is being currently deployed at a pace of 120 satellites per month and is months away from providing service. They have already started beta testing. Most of these constellations bank on laser intersatellite connectivity for long-distance data transfer possibilities. Products offering laser intersatellite links or ISLs at 10 to 20 G at distances up to 8,000 kilometers are already being advertised. Multi-gigabit laser ISLs have been demonstrated successfully on multiple occasions in the past. These are usually silicon carbide components mounted on the satellites and are discussed in the initial FCC filings of SpaceX. End-to-end paths in constellations supporting ISLs would consist of a radio uplink from source S to the ingress satellite, followed by 0 or more laser ISLs, and then the egress radio downlink to the target T. Two positional papers at HotNets 2018 discussed the utility of having ISLs in these new space LEO constellations. They showed that by virtue of speed of light laser, end-to-end latencies would be reduced significantly compared to today's internet. Let us see this in action. In this example, we are seeing a path between Zurich and Mumbai over satellites, which is quite close to the geodesic compared to fiber, which is roughly 2x longer. The speed of light being roughly 2/3 in fiber compared to free space means that the fiber path will be 3x higher latency. Despite this high bandwidth low latency ISL promise, there is substantial uncertainty about whether or not they will successfully incorporate ISLs. One hurdle may be the burn on re-entry requirement that regulators are asking operators to satisfy, thus not risking injury and damage from deorbiting satellites. In response, Starlink's filings were amended to exclude mention of these components. None of the hundreds of already deployed Starlink satellites feature ISLs. Luckily, LEO networks do not need ISLs to provide service. One might think, how to achieve long-distance end-to-end connectivity where there are no ISLs? Remember, as the constellations are being rolled out, ground terminals would also be rolled out. These terminals include user terminals on land and those mounted on airplanes and ships, and also more powerful ground stations. Without ISLs, connections between far separated ground terminals bounce up and down between satellites and on-path terminals, yielding bent pipe or BP connectivity. What is amazing is that latency lower than terrestrial internet can be often achieved over long distances even with this restricted BP connectivity. Mark's paper in HotNets last year focuses primarily on such latency benefits. However, in this work, we quantitatively show that even with dense ground station deployments, there are three very significant downsides to foregoing ISLs. Although LEO networks without ISLs still provide low latency between many ground locations, the temporal variation in latencies increases substantially. The network-wide throughput decreases heavily, and the network becomes more vulnerable to weather disruption because of transit through satellite ground links. We also analyzed the hybrid approach, which uses both ISL and BP connectivity in end-to-end paths. For running our simulations, we use Starlink's first shell, which consists of 72 orbits and 22 satellites per orbit and operates at a height of 550 kilometers and inclination of 53 degrees, and Kuiper's first shell, which consists of 34 orbits and 34 satellites per orbit and operates at a height of 630 kilometers and inclination of 51.9 degrees. At each of the 1,000 most populous cities, we place ground terminals, which are traffic sources and sinks. We pick 5,000 random city pairs for our experiments. Also, GTs, which only transit traffic, are placed uniformly every 0.5 degrees on the latitude-longitude grid within a radius of 2,000 kilometers of the cities. In addition to these GTs, to help BP achieve transoceanic connectivity, we use all in-air commercial aircraft as GTs. For this, we use flight average data for a period of 1 day from 2018. For the latency and latency variation results, we simulate the network for 1 day. At every 15-minute snapshot, we find shortest paths between the 5,000 city pairs. As seen in the plot, the minimum RTT is strictly lower for the hybrid approach as expected, although they are mostly comparable. There are, however, substantial differences in the tail, the maximum difference being 57 milliseconds. With exclusively BP connectivity, some paths see high latencies due to suboptimal intermediate hops. Next, across time snapshots, we compute the max minus mean RTT difference for each city pair and show the distribution across city pairs. The results show that latencies vary much more with exclusively BP connectivity. While with hybrid connectivity, the maximum range of RTTs across city pairs over time is under 20 milliseconds, with BP, this range is as high as 100 milliseconds. With BP, the path between Maceió in Brazil and Durban in South Africa sees an inflation of 100 milliseconds over time. This is because the density of air traffic is much sparser over the South Atlantic than the North. Hence, the path often ends up using aircrafts flying over the North Atlantic as intermediate hops. Note that this behavior not only inflates the RTT of this path significantly, but also makes the heavily used paths over the North Atlantic even more congested. Let us now compare the aggregate throughput offered by LEO networks with BP-only connectivity and hybrid connectivity. For each of the 5,000 city pairs in our traffic matrix, we route traffic over the k edge-disjoint shortest paths. Traffic between each city pair uses k subflows, each along one of these k paths. These subflows are treated independently by the simple max-min fair share algorithm, which iteratively and greedily finds the most congested link in the network and shares the bottleneck link capacity fairly among the competing flows. ISLs are 100G and up and down radio links are 20G. For only shortest path routing, the hybrid approach achieves more than 2.5x higher throughput than BP for both Starlink and Kuiper. While with k equals 4, this improvement is even larger, at least 3.1x. Besides the use of scarce GT satellite capacity for transit, in addition to only sourcing and syncing traffic, another reason BP fares poorly on throughput is that at any time, it is unable to utilize a large fraction of the satellites for networking at all. For Starlink, we find that across a day, the number of satellites that are entirely disconnected from the rest of the network varies between 25% and 31.5% of all satellites for BP connectivity. For analyzing the impact of weather on satellite connectivity, for each of the 5,000 city pairs, we find the shortest paths using Dijkstra's algorithm. Next, we find the worst attenuation seen across all links in the path. For paths consisting of ISLs, this value is either the first or last hop attenuation, whichever is worse. But for BP paths, this is the worst attenuation seen across all links of the zigzag path bouncing between the satellites and GTs. We use the ITU RPi library to measure the attenuation for GT satellite paths. The library implements ITU recommendations to model atmospheric attenuation due to rain, cloud, gaseous cover, and tropospheric scintillation in slant paths. For the ISL paths, we exclude GTs as intermediate hops in order to quantify the maximum improvements in attenuation possible with ISLs. We assume that the signal for BP paths uses error correction and regeneration at each GT. Otherwise, the multiplicative impact of attenuation would be prohibitively high. The Delhi-Sydney path covers the tropical region which experiences high annual precipitation. The heat map depicts 99.5th percentile attenuation across Southeast Asia. Although both endpoints, Delhi and Sydney, are in low attenuation areas, BP ends up using intermediate hops in regions with higher attenuation. In contrast, the ISL path avoids the entire high attenuation region. This plot shows the attenuation along the path. Y-axis plots attenuation and x-axis plots the percentage of time the attenuation value is exceeded. At least 1% of the time, the BP attenuation is 5 dB while ISL attenuation is 2.2 dB. Note that 1% translates to 88 hours per year. There are various other benefits of ISLs which BP struggles with, which I briefly touch upon. BP connectivity between certain sources and destinations is bound to require ground terminals in countries and regions that an operator would like to avoid, either because of challenging topography or due to political reasons. Ka and Ku band radio spectrum for the up and down links needs licensing. In contrast, thanks to the narrow beams and negligible interference issues, inter-satellite laser connectivity is unlicensed. GSO satellites fly above the equator and operates in the same frequency bands sought for LEO communication. Thus, LEO satellites, when crossing the lower latitudes near the equator, must avoid interference with GSO satellites. While GT field of view is already restricted by the minimum angle of elevation, GSO arc avoidance makes this field of view even more restricted. The impact of this will be much higher on BP than on ISL connectivity for traffic between the northern and southern hemisphere. Here is the latest update on the status of ISLs. In their September 3 launch video, a SpaceX personnel announced the testing of laser ISLs in LEO. But a lot of uncertainties regarding ISLs still exist. What would be the link capacities in practice? Link setup is constrained by the fact that it takes a few seconds to tens of seconds to establish these laser ISLs. How do we connect satellites using ISLs, keeping in mind the constraints? Our CONEX 2019 paper attacks this problem. Our work is also relevant for constellations like OneWeb, which do not plan to incorporate laser ISLs at the moment. It will be interesting to see how these constellations evolve with time and stand by their promise of global internet connectivity. With that, I thank you for listening.